So my name is Daniela VIEIRA. I'm the applications engineer at DeLong Instruments, and our office is in Montreal, DeLong, America. So first of all, I'm an engineer, so it's very far, like all these thoughts from my background. I may say some words that are not the right ones, but the main goal is to show you how low voltage can be like another tool for pathology applications, okay? So just briefly what we will be talking. So introduction, low voltage, our hypothesis, low voltage in pathology, and the conclusions. Most of you are very familiar with this, but we have light microscopy and electron microscopy for morphological evaluation. So light microscopy, it's very accessible, but it's limited in somehow like in the resolution, so you can't really see ultrastructural information. Electron microscopy, we all know the capability of electron microscopy. We can see deep details and we can see morphology that we are expecting some disease. However, now electron microscopy is not accessible, right? We see the high cost, the complexity of the equipment. It's kind of like a lot of labs, they can't have access anymore. Especially in pathology, when we talk about transmission electron microscopy, we know that like it can diagnose different types of disease, neoplasma, tumor, or identifying abnormal structures. However, it's in renal biopsy that we see most of the applications for EM. So GBM, other structures, or any type of deposition or fingerprint structures, all this can be identified with electron microscopy. So the current challenge when we are talking about transmission electron microscopy, so we do have the standard conventional electron microscopy. They usually operate at 100, 200, 300 kV. They are good equipment. However, we all know that they are expensive, very complex installation, and sometimes expensive maintenance too. And I got this paper. It's not a updated paper. It's from 2021, I think. And it says like still in that time was not really abroad. Like people did not have access to TM, and now it's still the same. So they have this review where they saw a lot of pathology papers in the clinical scenario, and only 70% had access to EM. And within this 70%, 77% had like really good information from EM pictures. So the idea is like, let's make it more accessible. And another challenge for the standard electron microscope is the contrast. Of course, we all use here like uranyl acetate or different types of stain, but still like you need to have some type of uranyl based stain to provide high contrast and be able to see. So low voltage, what it means. So instead of operating at 100, 200, 300 kV, we are operating at 25 kV. So we see like in here in the first picture, the main advantage of low voltage is the highest contrast. So for the same type of material, as you increase the voltage, you decrease the contrast, right? And that's because the interaction of the electrons with all the sample, like with the sample, is different. So in here, we see at 25 kV, we have much more interaction. That means we have a higher contrast. At 120 kV, it goes in one way. So you don't have interaction, you don't have contrast, you need to stain, okay? So at low voltage, we have the higher contrast due to the interactions. In our specific equipment, we use permanent magnetic lens. That means we don't need a cooling system, and we can make very compact systems. And we still can provide a resolution of 1 nanometer, which means like it's good for almost all the pathology applications. So we are talking specifically here in that presentation, the LVM25E. So it's a transmission electron microscope that operates at 25 kV. You can also have a stain detector added to that transmission electron microscope operating at 50 and 10 kV. So that's the real size of the equipment. No anti-vibration platform, no cooling system. You can place it in any lab. There's no facility requirements. And again, just the advantage, so flexible staining protocols. In this presentation, we will be seeing some standard uranyl acetate, but we will also see some uranyl-less, and you also have the capability to do unstained samples at low voltage. So smaller instrument, you can place it in any place, lower complexity, and reduction of the cost as well. I will be discussing it in the next slides. So our hypothesis is, can low voltage TM deliver diagnostic grade pathology imaging without compromise? So in here I have a lot of different cases that I will, as I said, most of the nomenclatures I'm not really familiar, but you guys are familiar and you will be seeing the results of low voltage electron microscopy. So the sample preparation is exactly the way you guys are used to do for the standard TEM. So same thickness. You have the flexibility to use uranyl-free stains or unstained sample, but the traditional uranyl acetate is also pretty much useful in here. So in this presentation, I do have some, for example, this is a standard uranyl acetate image, but during the presentation, you guys will see most of uranyl-less, so alternative stains, okay? So as you see, similar protocol to produce the thin section, similar thickness, and then here the only thing different is the stain. So muscles and some mitochondria. Same flow of image, so you have very low mag where you can identify where is your thin section, then you go low mag to see, then you go to different types of magnification. And then at some point you can go to 20,000, you go 700,000 times if you want with that microscope, and then you can start to see details. So all these pictures in here, they are uranyl-less, so not uranyl acetate, okay? Another example, it's nerve. Again, this is a uranyl acetate picture, but the ones that I will be showing different magnifications, they are all uranyl-less. So same flow, we have very low mag, you can identify where your thin section is, then you just go higher magnification as you need. So in here we have some nerve, and I know it's important to see this a distance between these layers. So we can show here that it's 60,000, but you can go above if you need more details, okay? In kidney, as I said, 25% of the pathologists, they use EM for kidney. So we do have a standard uranyl acetate, and then inside uranyl-free. And we can see structure as podocyte, dense deposits. And in our next slide will be more about the amyloid fibers. So amyloid fibers here, we have a standard uranyl acetate. And when we are talking about these small details as amyloid fibers or other higher magnification that you need, uranyl acetate will be better than uranyl-less, not because of the contrast, because the contrast at low voltage is fine. It's much more because of how sharpened the pictures can be when you are using uranyl acetate. However, you will see that it's still comparable. So if you are not talking about a publication or something like this, you can still see the amyloid fibers using uranyl-less. So that's uranyl acetate. And then in here, it's uranyl-less. So different magnifications. And by the end, the last picture is where we can see the fibers, but not clear as when we use uranyl acetate, okay? Same example will be for the ciliary. So that's uranyl acetate. So you see much more details. When you go to uranyl-less, still have you can still see them, but it's less. That's not because of resolution on microscope, it's because of the stain, because we can compare uranyl acetate or uranyl-less, and you see. But what we want to bring when we bring like the uranil reef, in US, I'm not sure if it's a problem now, but most of the countries, they can't use uranil easily as was before. So that's why it's good to see that, like, even if you're not having the best detail that you want, you can still use uranil less and you can still see the details that you want. Another example, holy blood, that's also like uranil less, and some liver. So our idea is in here is like to bring most of the common pathology sections, so you guys can have your eyes and see like different applications for low voltage, okay? So I asked like, can low voltage deliver diagnostic grade pathology? And yes, LVM can do it. So we can see the details that we need for different types of pathology, different types of sections. The main advantage, I know low voltage is like our main advantage, but sometimes for your application today, we have so many softwares that you can have it from softwares or AI, but the size and the simplicity of low voltage, you can't have using any software. So that's one of the main advantages of low voltage for pathology applications. And it's much simple in terms of operation, much simple in terms of maintenance, especially because we don't have cooling systems. Ours, like everything is different than a standard, a conventional TEM. That's just like a little bit of comparative numbers. The prices are all estimative. I'm not completely sure. You guys know more because you guys buy the microscopes. So when we talk about the standard 100, 200 kV, GO and high-touch, they are the main, like both the being used in many labs. So they have a very good resolution, but as I mentioned, like not really applicable in that specific application. If we are talking about materials, development of different things, then yes, but in pathology, biological, 1 nanometer is more than enough for most of the samples that you guys have. The footprint, it's even not comparable. It's totally different in terms of installation, in terms of complexity, and where you can place it. You can place, like, I have some customers in the 4th floor, and like the microscope is working very well. So in terms of price, we usually say about half price when you are acquiring your microscope, but in here, you don't need to include any type of facility, right? So no anti-vibration platform, no cooling system, you just plug it and that's it. And then when we talk about maintenance, because of the simplicity, we talk like 100 in 10 years and let's say 10,000 per year. And the others, usually it's about 10% of the cost of the microscope for maintenance. And installation cost is like, it's really zero for low voltage. And when you compare to this like a high voltage or like a standard conventional system, it's like you really need to prepare the entire room for that. We published these 3 articles in the Microscopy today. So they explain more how the machine works, what is behind the technology, also some applications. And the last one is when we are more like related to teaching, because of like, it's so easy to understand, so easy to operate. We have a lot of professors using it as a teaching approach. So that's Dr. DeLong. He was the inventor of the technique. And when he was doing it, when he was making the microscope, he was like, every scientist should have a microscope, an electron microscope. Yeah. And I personally, I really like it. I agree completely with his idea. He was not like, he did not want to sell it. He just wanted to make it accessible to all of like scientists. We have some users. These are only in the pathology field, but we have microscopes all around the world in different types, in different fields. Our factory is in Czech Republic, so it's all electron microscopes. They are basically made in Czech Republic, and our international office is in Montreal, in Canada, and we provide service to the entire US. Thank you so much, guys.
The only thing I don't think you mentioned in detail is the service. What kind of service you have available?
So you don't really need a service. When we say about cost maintenance, it's just the change of the cathode, and that will be similar for any type of electron microscopy. But all the alignments, you can do it by yourself. So during the training, I teach you how to do it, and then you can maintain it.
But if you need service, if you need problem, you don't know.
Then you contact us, and then we come here. Like we are in Montreal, we provide service to US, but you don't need to have a service contract with us. No, you don't need. Like it's not. You can have warranties if you want, for sure, but there's no service contract.
So, can you repeat the price?
We say about 450. 400,000.
I have a question. May I ask? A question is this. I've seen that in your picture, the thickness of the section, ultra thin section, is about 90 nanometers. So I would like to know if is the request from this kind of microscope, because usually with the conventional transmission electron microscopy we use a thinner section, about 70 nanometers. So I think that the thicker is due to the low voltage, and also because you don't use the uranyl acetate to make the counterstain of the section. Can you explain this?
It's actually like we say a standard, but if you do 70, 50, it will work even better, I would say. Our limitation will be around 120 nanometers. Above it will be hard for you. That is a sample from one of our collaborators. And then he is doing 90 using uranyl less. But we have many collaborations that we do 70 or 100. So it's really standard. So if you do 70, it will work perfectly well.
Okay, thank you.
David.
Yeah, very interesting talk. We had a nice talk yesterday from Rucheng Shah about environmentally friendly laboratories. And one of the points she made is that pieces of laboratory apparatus use a lot of electricity. So a minus 80 freezer sucks a lot of electricity, and electricity is in short supply now. So I would imagine that a relatively high voltage electron microscope uses a lot of energy, and your instrument probably uses less. Have you ever tried to do a comparison to see how much energy?
We actually have collaborations with Xing, and she mentioned it to us already. And I never calculate it, but the microscope, if you are not using, it's off. Like you turn on and you turn off the electron source all the time, because it takes like 1 minute to warm it up. Differently than the standard or the conventional system that usually you keep it on. But overall, it's less, of course. If no cooling system, all this, even like the room temperature, it's normal. Like you don't really to have a very like a controlled room temperature. So it's lower. But we never mentioned that it's like, let's say, nature friendly, because we never did any calculation, environmental friendly, let's say. But I would imagine, yes.
And the standard power supply, you just
a standard grid, everything. Yeah, it's exactly like a standard TM. The only difference is the low voltage, and because we can do 25 kV, that's why we can make everything compact and like it. It's a different design, but it works exactly like a standard TM.
You said you turn the thing off if it's not in use. What about the vacuum? Does it stay on?
It stay on, yeah. It's still like it's ultra high vacuum inside. The IP, we have ion pumps, and the ion pumps are on all the time. Yeah. Yeah.
What exactly is the disadvantage compared to TEM?
So the main advantage for this specific application is the accessibility. So the price is about half. So you don't have a service contract. Sorry. Oh, sorry. So The main advantage, resolution. So when we are talking about the standard conventional TM, 0.2 nanometers, 0.1 nanometers. If we are in the material science, for example, that's a big limitation, let's say. They need to see atomic level resolution, right? Or some like very small proteins you are not able to see at low voltage. Everything above 5 nanometers, you have a very, very, very good picture. If you are near to 1 nanometer, it's too close to my limitation. So you may be able to see, not clear as you were expecting. But that's the main advantage. The resolution is the main advantage. Yeah, disadvantage.
One question.
Hi, sorry, I have a question. Sorry to interrupt. Do you know if there are this kind of microscope in Paris region, or did you sell to any lab in France?
Sorry, I did not hear you.
Sorry. My question is, do you know if there is this kind of microscope in Paris region in France?
Yes, I know we have a lot in Europe because the factory is in Czech, but I'm not responsible for Europe, so I don't know exactly where they are. I'm responsible for the entire world, not Europe. But I can contact them and then tell you. But I'm pretty sure we have 1 or 2 in Paris, if I'm not wrong.
That's good. I will drop you an email. Thank you.
So, it seems these days our main interaction with the TEMs are through the camera software. And can you talk a little bit about the camera and how the image acquisition system that works? If that's something that's operatable in the future, that sort of.
So the way it's a little bit different than the conventional too, because the way the microscope is built. So usually we see that big like towers, like the columns, because the electron source is on the top and the camera is on the bottom. In this system, it's the opposite. So the electrons, they come from the bottom to the top. And then we have a YAG crystal. I know now I'm like engineer here. We have a YAG crystal. So everything that is detected is actually photons, not electrons. So it's a CMOS camera. So it's a very, very different system. Also, the advantage is like price is less expensive because you are detecting photons, light, instead of electrons, because of this inverse system that we have. Like this technical part, if you guys are interested, the papers are the best way to really understand, or you can talk to me and I can show you how the design is completely different than the conventional TM. But what it's important to understand here, that is transmission electron microscopy. So it works exactly as a TEM, it's conventional TM. It's not a STEM detector in SEM or like some kind. So acquisition time is exactly the same. Sample exchange 2 minutes. So it's pretty much exactly like a conventional TM.
So the camera is a part of the entire system.
Yes, it's part. So if you see, let me just go back to the slide. I have so that's the entire system. You just need that space. So that's the microscope and that's just the table. So in here, it's where we have the column and the camera. It's like about that size here. It's really compact compared to the conventional, especially because of the lens. So we don't have a cooling system. It's a different type of lens. It's a fixed potential. So it's 25 kV. You can't modify to different voltage. It's always 25 kV. That makes it more compact.
Well, if there's no more questions, thank you very much.
Thank you so much.